Hello! So, in this video, we're going to be doing Cauchy's condensation test, meaning that it condenses down the series into sort of a subsequence of that series, okay? So, what I'm going to do, so this actual proof and this theorem is not too bad in terms of sort of what's happening once you know what's happening. So what I'm going to do is I'm actually going to start out by doing sort of an idea sketch of the proof, and then some editing magic, and then I'll do the real proof. But I'm hoping that the sort of idea sketch that I do should help mitigate the alphabet soup, the algebra that happens when we actually have to go through the nuts and bolts in the proof. So I am going to do a real proof of this that will be in this video, but I'm going to start out with sort of a hand wavy, here's the idea of the whole thing, okay? All right, so to be very clear with that then, let's start out with the idea as opposed to the proof. So what this test or this theorem is claiming is that if we want to know something about the convergence of the ANs, we can know something about that convergence or divergence by looking at only some sort of sub-piece of it, some terms of the form a to the a sub 2 to the n. But this does require that eventually, remember what that means, right? That means that for some, it happens at some point in, right? There's some capital N such that for all little n past that, this will hold. So this is just saying that these things are decreasing because they're non-negative real numbers, right? So we have some sequence of non-negative real numbers, so positive numbers are 0, and it is eventually decreasing. Then we can look at this subsequence piece that's weighted, and looking at only those terms, we can know something about the convergence of the whole thing, and vice versa, right? Convergence or divergence. So again, this is one of those things that's sort of easier to see if we actually see it happening. So the idea here is that, let's say we're at the point where we are sort of decreasing, right? So let's just say this is happening right from the very beginning, so we don't have to worry about the eventually part. Let's, for the moment, suppose, right, that it's just happening starting at A1. So if I were to do something like Sn, right? Well, Sn, if we remember our definition, right, this is just A1 plus A2 plus A3. I'm going to write more than you would expect because I'm going to be doing something with this. So A5, A6, A7, A8, A9, A10, etc. up to a capital N, okay? So this would be if we were looking at this thing. If instead we wanted to think about this thing, the key idea here is that because this is decreasing, right, and I'm supposing for the moment that it's decreasing right at the start, specifically A1 is bigger or no smaller than, because they could be equal, A2, which is itself no smaller than A3, etc. So I could sort of overestimate by replacing some of these with any term that came before it, right? So like if I replaced A3 with A2, A2 is no smaller than A3, so I've only made things bigger, right? So I could, for example, if I wanted to, write this as still A1, that's fine, A2, but then instead of A3, I could write A2 again, right? And so I've only replaced it with something bigger, right? I replaced the smaller thing with the bigger thing. And then I could skip A3 entirely, just go straight to A4, because A3 is the thing I've replaced, right? So I could look at A4, but then I could replace a bunch of A4, a bunch of stuff after that with A4. And again, I'm only making things bigger, right? And I could, again, stop anywhere I wanted to, right? I could replace A8 with A4, but for reasons, which we'll see in a second, I stop there. Now I'm going to use A8, right? But now I could do A8 for all of these things, right? And eventually I get up to some AN thing. I'm not going to worry about the dot 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 bit because the part I want to focus on is what's happening in this short term, okay? So if I look at what's happening here, this is just A1 plus, now I have two A2s, And I have 1, 2, 3, 4 A4s. Oops. Might help if I actually wrote the thing I said instead of skipping ahead on myself here. I have 4 A4s. And then if I did this sort of in the right way, as we would expect, I'd get 8 A8s, etc. Right? But I can notice here that this 1 is really 2 to the 0, right, in both cases. So 1 I could write as 2 to the 0, A sub 2 to the 0. Here I have 2 to the 1, A sub 2 to the 1. Here I have 2 squared, A sub 2 squared. And here 2 cubed, A sub 2 cubed. And so here, this is exactly what's going on in the condensed version, right? I'm taking some weight, but what that weight really is how many terms I sort of replaced with that first term the whole way through, right? So I've replaced 2 to the second 4 of the things with A4, starting at A4 and going forward, right? So I have A4, which I'm replacing or keeping as A4, but then I replaced A5, A6, and A7 all with A4 because A4 is bigger, right? So if this thing converged, right, if this converges, say to some t right now, meaning this line, if this line converged, right, as n goes to infinity, well, this thing, this t, is going to be an upper bound for Sn. And Sn, being a sequence of non-negative real numbers, right, is an increasing sequence because I keep adding non-negative things to it. So it's an increasing sequence with an upper bound, which would tell me that Sn converges, right? So in some sense, it shouldn't be too surprising that if we know that this thing converges because of literally how we're building it, we're just replacing smaller things with bigger things. If we know this thing converges, getting that the first thing converges should be pretty straightforward. But the other direction, knowing that Sn converges implies this other thing, this series of 2n, A sub 2n converges. That is questionable, right? Because on the one hand, a to the 2n, right, if I'm taking further and further pieces out, you know, a to the 4th, a to the 8th, a 16th, a 32nd, etc., I'm taking far down pieces in the sequence, in the an sequence. And if Sn converges, that an sequence is going to 0. So this piece here, this piece, if S capital N, if the original series converges, this thing goes to 0. But at the same time, this thing is going up to infinity as n goes to infinity, right? So I have some fight going on here between something getting small and something getting big. So it's not really clear on first glance that this thing should converge if that thing converges, okay? So really the hard direction here is going forward, not backward. The backward one isn't too bad. It's the forward one that might seem a little weird. And this we're going to do with some algebra trickery, basically. So I'm not going to explain this yet. I'm going to do this in the actual proof, but I'm trying to point out the idea that the backwards implication, which is the one we'll start with in the proof, that one isn't so bad because all I'm basically doing is getting an upper estimate and then assuming that that upper estimate converges and using the fact that that is an upper bound to say that this increasing sequence converges, and that's not so bad. But the very fact that this is sort of by definition bigger than that thing means that this thing is hard to know just because this has to be bigger, that it's going to converge knowing that the smaller thing converges, right? Like normally with a comparison test you can't conclude that, right? If the smaller of the two sequences converges, you don't necessarily know anything about the bigger ones. So that's where the work is going to come in. That's the algebra trickery, okay? All right, so that's the idea. The backwards way, we're going to use the fact that this is inherently larger, so if it converges, it gives us some upper bound, which will give us that the original converges. And then the other direction, there's going to be some, as I say, algebra trickery in order to show, I say trickery, but it's legit, but it's going to be some algebra effort to show that the other direction holds, and that's going to be the hard part, okay? All right, so I'm going to do my editing magic, and we will see how this goes. So, abracadabra, and we're back. All right, so, as mentioned, we're going to start the proof. Now, we've already, in other proofs, shown how to deal with this eventually thing. So the first thing I'm going to do is I'm just going to assume, without loss of generality, suppose an plus 1 is less than or equal to an for just all of these n's for n greater than or equal to 1. Something I forgot to point out when I was reading out this thing, just to be clear and careful, note the indices here, right? So the first thing, just the an, started at n equals 1. So here it starts at n equals 0, but that's really because I'm using powers, right? So 2 to the 0 is 1, that's why this has to be 1. If this were starting at 0, I could do something like this, but I have to peel off the a0 piece on its own, because this is only going to start at a1 sort of by it the way it's designed. So just be sort of aware of those indices. All right, so without loss of generality, I'm just going to suppose these ANs are just always decreasing from the very beginning. Like I said, we've seen in other proofs how to deal with that with the capital N, little n bigger than that, blah, blah, blah. All right. The next thing I'm going to do is just give some notation to deal with these things. So the first thing, like I said, we're going to be actually going this way. So I guess I should prove I'm going that direction. So I'm supposing that this thing on the left, thing on the right converges. So here I'm going to denote the sum. So like I said, I'm just going to do a bunch of notation up front just so we're all on the same page. So from n equals 1 to n of an, this thing is going to be defined as Sn, like our normal thing. I'm going to let Bn be the individual terms here. So this is 2 to the n, a sub 2 to the n. And I'm going to make the n going from now 0 to capital N of Bn. This I'm going to call capital Tn, right, instead of Sn. And we're supposing that this thing converges, I'm going to say to T. Okay, so we're supposing, right, that this thing converges. I want to conclude that this other one converges, so I'm going to say specifically converges to T. Okay. So if remember from the idea stage of this, what I want to be able to claim is that T is going to be an upper bound for all of it, all of the n's, like Sn for all capital N, right? So that I can have some upper bound on that sum and conclude that it has to converge. So to justify this, I have to sort of formally do out the idea stage that I was talking about. So first I'm going to observe, so observe for any, let's say, n and k, if I take the series, let's use subscript, actually let's do m here, there we go. This will make it hopefully a little easier to read. So if I start at m, and I go to m plus 2 to the k, so if I take a sub n, then this is what I'm saying here is I'm going to be adding up all of the numbers from some starting point, and I'm going to go 2 to the k more than that, right? But the claim is that if I replaced all of those 2 to the k with what was ever the first number, that I would have something bigger. So this is less than or equal to the sum, and this is why we have to be real careful about subscripts. So it's the same sum, n equals m, and m plus 2 to the k, but now it's going to be a sub m. So again, to be real clear here, n is the index variable, right? So here the index variable is actually playing a role because I'm adding up different a's, right? A sub m plus 1, a sub m plus 2, etc. Here I'm not adding up different different a's, because I'm adding the same a sub m a bunch of times. In particular, I'm adding this up 2 to the k times, and they're all a sub m, okay? So in particular then, remembering how I have defined my bn's versus an's, right? If I look at, say, the sum of, starting at some point, so let's say n equals some value, so 2 to the m to the 2 to the m plus 1, right? So basically here, my starting point, I'm looking at 2 to the m. So if I do 2 to the m plus 2 to the m again, I'm going to get 2 to the m plus 1, right? So I'm saying if I go from now that specific point and do another 2 to the m of a sub n, that this is less than or equal to, well, this first thing is a to the 2m, so I'm going to be doing the sum, n equals 2 to the m to the 2 to the m plus 1 of a, and then the starting point, 2 to the m. But this is 2 to the m plus, right, so if I went from 2 to the m, I did another 2 to the m, that's up to here, so I have 2 to the m of the a sub 2 to the m, which is b sub m. Okay? So this is why I said there's like an alphabet soup to do this formally, but what I'm saying is if I look at a block of some 2 to the whatever power long, in this case 2 to the m, right? So if I think about, let's say m is for a second 2, right? So let's just do this off to the side as a concrete example, so I can show you what's happening here, because it's really easy to get lost with all these indices and all these things, right? So if I look, for example, when m equals 2, what am I doing? I'm going from n equals, well, 2 is going to take too much space. Let's do m equals 1. Hopefully that'll still show. So if m equals 1, I'm going to have 2 here, and then 2 to the 1 plus 1 is 4 of a n. So what is this? This is a2 plus a3 plus a4, right? Okay. Did I mess something up? Oh, yeah, sorry. I did mess something up. Sorry. This is actually going to be the start of the next thing, right? So I have, if I go from m to m plus 2k, that's actually 2k plus 1 terms, because I'm getting the first thing on the next one, right? I want a power of 2 as the number of terms I'm adding. So there should have been a minus 1 here. I'm sorry. And that is actually 2 to the k terms that I'm adding, not 2 to the k plus 1. So I should have a minus 1 here. There we go. Whew, that was close. Glad I decided to do this example, otherwise that would have been really confusing. Okay. So the claim is that this is less than or equal, taking, again, the sum, n equals 2 to the m, which m was 1, right? So I'll be specific, m equals 1 here. And this was 2 squared minus 1 is 3. There we go. So again, I'm going to start from n equals 2 to, again, 2m, I forgot another spot, sorry, minus 1, minus 1. There we go. Consistency is key. All right. There we go, right? I only want to add a power of 2 number of terms together. So here, I'm going to go from 2 to 4 minus 1 is 3. But now I'm doing a sub 2m, so a2. So this is now, I do it once at n equals 2, once more at n equals 3. This is a2 plus a2. And again, the claim is that this is going to be 2 to the m, so 2 to the 1, times that first term, a sub 2 to the 1. And that claim is that it is, right, I'm doing the question marks for all of these signs, and then we'll verify. The claim is here that this is B1. Okay? So let's take a look and make sure all this makes sense. So here, 2 to 3, so add in, put in 2, put in 3, that's good, right? The claim is that this is less than or equal to this thing, but this thing is just this. So all I've done is replace the A3 with the bigger A2, right? Because I'm assuming that it's true right at the start. So this is indeed bigger, right? So this is good. And the claim is that this thing is equal to 2 times A sub 2. That's true. And that thing is really B1, which should be 2 to the 1, A 2 to the 1, which is exactly what it is, okay? So although there's a whole horde of craziness going on here, right, with the indices and the +1 and -1 and all the insanity that's happening, what's actually happening is not that complicated. It's just really hard to write down the general term. That's what's going on, right? So this is just replacing the string of some power of 2 length piece with the first thing many times, right? And that was the idea that we mentioned at the beginning. Okay, so coming back here, why do I care? Okay, so what this is saying then is that, so looking at, let's say Sn, but I want to use just any n because I want it to work out nicely. So I'm going to use some capital N that translates nice into these Bn forms. So I'm going to look at S sub 2 to the n. Basically, I'm going to look at the piece far enough out on the ANs that it's going to look like these BNs nicely, is what's going to happen. So this thing then is the sum, little n going from 1 to 2 to the capital N of AN, right? So the way you want to, or the way you can think about this is that this thing is really, I'm going to break it up into these pieces the whole way through. So this thing here, right, this was sort of starting going. So what I'm going to do is look at this as m's. So I'm going to write this out sort of longhand so it's clear what's happening, or hopefully it's clear what's happening, although again it'll be easy to lose it in the soup. So this is going to be the sum, so this will be sort of the stupid sum, but this will be the sum n equals 0 of 2 to the n a sub 2 to the n. And this is going to go from the starting point to the first binary, the first power of 2, which is only of length 1. So I really actually only want one term here, which is why this is the stupid one, right? It's only going to plug in 0, but really what I'm saying here is this is just a1. But I'm doing that because I want to show how it's going to keep going. All right, so I didn't need to write all this, but I'm doing it so you can see the pattern. The next one is going to be n equals 1. And then this, so this was a length 1, so I want a length 2 here. So this is going to be up to 2. And this is going to be, sorry, I shouldn't write that. This is going to be, in fact, let me even do this. What I wrote there was right, but let me do, yeah, I'm skipping ahead. So what I was writing was correct, but let me do an intermediate step and maybe that will make it clearer what's happening. So If I just jumped ahead, it's because I did some editing magic and I was going to do a thing, but now I'm going to sort of step back and do a little bit more, so hopefully it's clearer for you guys. So I can start at 1 and sort of end at 1, which seems dumb, but there's a reason behind the madness. Bear with me. And the reason is I want to break this up into the number of terms I'm summoning. This is going to be 2 to the 0 terms, which is just one term, which is why I'm doing that. This next one is going to be 2 to the 1 terms, and it's going to be the next ones. So this is going to be the next one, 2, but I want it to be of length 2. So I want 2 and 3, AN. And then my next one should be 2 squared terms. So I'm going to start at 4, and I'm going to end at, if you can't tell, right, like 1, 2, 4. Next one's going to be an 8, so this will be 1 shy of that, right? That's how I'm doing this, AN. So then this is going to be n equals 8 to 15 AN. But this is 2 cubed. That's how many terms are there, right? So I'm not actually changing anything. I'm just grouping it apart so you can see what's happening. Oops, not equals. And I'm going to keep grouping this in such a way that my last one, I guess if I'm doing it this way, I should have -1, I guess, to make this end nicely, right? So my last term is going to be n equals 2 to the power of n minus 1 up to 2 to the power of n minus 1 AN. Okay. Now, why am I doing this? Well, now I can apply this thing. Each of these things, right? Each of these is what's happening. So if I look at, say, m equals 0, I have 1, and then when m equals 0 here, I'm going to have 2 to the 1 minus 1 is 1. So that's exactly, right? This is exactly when m equals 0, m equals 1, m equals 2, m equals 3, m equals capital N. Okay? But I know I can take each of these things just as their sums, right? The whole sum is less than or equal to bm, the term, meaning that I can write this as b0 plus b1 plus b2, not the sum of the b's, but the actual term b, right? Plus b3 plus up to b capital N. But this is just T capital N, right? And so here I've shown that my S2 to the N is, and I'll highlight this in a different color so it stands out a bit. So my S2 to the N is less than or equal to T to the N. Right? And I will point out sort of one other thing about the fact. So here I said T to the N converges to T, but remember these things are all non-negative. So T to the N is an increasing sequence, meaning that it increases to T, meaning that T to the N is less than or equal to T for all N. That appears to be off screen, so let me write it down here. So this thing is less than or equal to T for all N. I just realized that I went through all the talk about this thing and I'm not even sure you can see it. So this is B1 is what I was saying here, and that worked and that worked. Sorry, I didn't realize it was off screen. I gotta fix the cropping on this studio. Okay, so all of this soup, again, I understand there's a lot of numbers, letters, and craziness going on here, right? If you need to, go back and look at the idea again, just like we did sort of at the very beginning. What we're doing is that we're breaking these apart into pieces of length 2, and then replacing it, each piece, by adding up the first term that length number of times, right? The 2 to the m, a sub 2 to the m, right? So here we're replacing a2 and a3 with a2 and a2, and that is, weirdly and confusingly, b1, right? Because b1 is really 2 to the 1, a sub 2 to the 1. So what I've done here is the technical sort of nuts and bolts, getting your hands dirty version of what we said in the idea, which is that this shows that Sn is less than or equal to t for every n, meaning that I have a uniform upper bound, right? So t is an upper bound for the increasing sequence, and that's also important, right? S capital N, right? And again, I know I've said this a bunch, but just be very clear, all these terms are non-negative, so Sn is an increasing sequence. It's why we can do this, right? Why we can say that since it's an upper bound, right? Thus, since t is an upper bound, Sn converges. And that gives us the backward direction, right? We assumed that this thing converged and concluded that the SNs, this thing, converged. And we're good, okay? So as I guessed, I'm gonna have to do some editing magic again in order to do the other direction. Okay. All right, so. Abracadabra. And we're back. All right, so as we saw, we did the reverse direction first, so I'm gonna do the forward direction now. Switch colors again. Hopefully it makes it easier to find parts of this video in the future. I'm gonna, again, without loss of generality, I'm still assuming that it's decreasing right from the beginning. And so, again, I'm gonna sort of off to the side do a quick little sketch of the idea, which is the same sketch, the same idea, but with a little bit of a twist. So what I'm gonna show, or what I'm gonna think about, is before, when we did something like, let's say, A1 plus A2 plus A3 plus A4 plus A5 plus dot dot dot, right? So before, what we did is we took A1, we let it be A1, and then A2 and A3, right, we replaced A3 with A2 because it was bigger, and we got an overestimate. But now the problem is that we're going this direction. We know that the original thing converges. We want to know about something about this converging. We want to use the same general idea, meaning we want to have a upper estimate. But that means that I don't really want to replace it with something that gets bigger, because I want this to be the bound. So instead of taking this sequence and replacing it with something and getting a bigger result, what I'm going to do is try to force a smaller result. If I just teleported, wow. So in order to keep this nice in the binary sense, meaning like I'm going to do this still with powers of 2, the idea here is that I want to replace it and make this whole thing smaller. And the way I'm going to do that is I'm going to leave A1 and A2 the same. And the idea is if I replace an earlier one with a bigger, with a bigger index one, right, one further down the stream, because it's a decreasing sequence, I'm going to get something smaller. So I'm going to replace A3, instead of replacing with A2 like I did to make things bigger, I'm going to replace it with A4 to make it smaller. So I'm going to look at this as A4 plus A4, right? I'm replacing A3 with A4. Likewise, A5 and on up to A8, I'm going to replace with A8, 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 A8. So A5 becomes A8, A6 becomes A8, A7 becomes A8, A8 remains A8, okay? So since I'm replacing earlier ones with later ones, I'm getting something that is smaller. So this thing is greater than or equal to this thing, okay? And I'm going to write this in a way that is similar to, but not quite the same, right? This is the algebra trickery I mentioned earlier, because I'm not getting this series, right? To get this series, I would have had to do it the other way, like I did the first direction we talked about, right? The first part of the proof. So here I'm going to get just A1 plus A2. Those are just hanging out by themselves. Specifically, I guess I can rewrite, and maybe I should. Well, no, I'm going to leave it like that. Pretend I said nothing. And then I have 2 A4s, and I'm going to have 4 A8s, and so on. Which now, if I do this by itself, A1 still by itself, I'm going to have 2 to the 0, A sub 2 to the 1, 2 to the 1, A sub 2 to the 2, 2 to the 2, A sub 2 to the 3, and so on. Okay? So I'm making this observation. If I just did a sum of numbers, right, the sum of the ANs, that would be greater than or equal to this version of that, okay? This is going to come up in a minute. So I make this observation. I'm going to stick it over there for a second. Okay. I'm going to use the same notation I did before. So just to remind you, Tn, so Bn is 2 to the n, A sub 2 to the n. And then S capital N, that's the sum up to capital N, little n going from 1 for AN. And now, just as we know, right, so now since we're assuming that direction, this thing is going to converge, let's say, to some S. Right, and my game plan is to show that that's an upper bound for something, and hopefully that's helpful, but we'll get there. And then finally, Tn, right, same as before. This is the sum, capital N, little n going from now 0 of Bn, okay? Okay, so now's the leap that you wouldn't maybe see to do on your own, and it's sort of the germ of how this proof is going to work, right? It's a sort of key idea or key thing about most theorems you learn, even in upper level math, graduate math, even research papers. A lot of the times, there's 1, maybe 2 true key ideas that make a proof work. And everything else is sort of going through the details, the consequences of that one good idea. So here's the idea, which is we're going to consider 1/2 of T capital N. Okay? Okay, so what is that? Well, 1/2 Tn, this is going to be 1/2 times, just to be, again, real extra clear here, B0 plus B1 plus B2 to Bn. But that's really just 1/2 times. So B0, that's 2 to the 0, A1, right? So it's 1A1 plus 2A2 plus, well, I'm going to keep it in powers of 2. We'll write this as, so that's 2 to the 1. This is 2 squared A4, 2 cubed A8, etc. Okay? But now I can put this 1/2 in. So here I'm going to have sort of this annoying first term. I'm going to write this as, I guess I'll just leave it as is, 2 to the minus 1 A1. But here's the important things. This is 2 to the 0 A sub 2 to the 1, 2 to the 1 A sub 2 squared, 2 squared A sub 2 cubed, etc. But now if you look at this, right? The A's are all non-negative. So if I replace this 1/2 A1 with a full A1, I'm only going to get something bigger, right? But if I take this whole thing and replace it with this thing, right? This was equal to that, was equal to that, right? If I replace it with this thing, I get something yet bigger. So what I'm justifying here is that this thing is in fact less than or equal to the sum up to whatever the last term is, which if I'm looking at T sub capital N is going to be something of the form A, right? So Tn, the last one's going to be B capital N, which is going to be 2 to the capital N. So this is going to be the sum, and going from 1 to 2 to the capital N, AN. That's what this thing was saying, is that this thing is greater than or equal to that, which is that, which is that. This is this, only a little bigger, because I have a full A1 and not half of A1, right? So I go from here to here, which makes it bigger, to there, which makes it yet bigger, which is that. But this is really just S sub 2n, right? And again, just like before, since these things are all non-negative real numbers, this is not just converging to S, but it's increasing to S, meaning that this is less than S, or less than or equal to S, I should say, for every capital N, right? S is a uniform bound on this thing. So in particular, I actually have that 1/2 Tn is less than capital S for every n, i.e. Tn is less than 2s for every n, right? But if that's true, I have, again, a uniform bound. That doesn't look like an S. Ooh, my S's are getting shoddy here. Sorry. So I have my sequence of BNs, right? I have this thing, the actual real sequence, not this weird morphed one. And I have a uniform bound, right? A bound that applies for every n. It's not S like I would have sort of expected or hoped, but it's close. It's 2 times S, and that's good enough, right? And so Tn is bounded above, it should be equal to, there we go, sorry. So Tn is less than or equal to 2s, which means it's an increasing series bounded above, so Tn converges. So even though this was sort of the direction that was a little bit of a wizardry of sorts, right? The part that seemed like it's harder, it is conceptually harder in that you need to think to do this, right? This is the step that makes everything work great. It is definitely the step that is mathematically less obvious that it should work. But it turns out it's also the nicer one to prove, right? It has a prettier proof, and that's a much more succinct and straightforward proof, unlike the alphabet soup version we went through with the last one. Okay? All right. So this concludes what is probably simultaneously one of the more intuitive and least intuitive theorems, right? It's intuitive in the sense that, like, we sort of expect at least one of these directions to be nice, and from a concept standpoint, it's nice, but from a notation standpoint, it's terrible, right? It's one of those things where it's often said that the easiest things to prove, the easiest things to sort of think of, the most obviously true statements are often the hardest things to actually prove. And that's sort of an example of that, where writing down the intuition is awful. All right, so with that, this video is done.